Okay. So very good afternoon to all of you. Let me welcome you again after post-Puja departmental seminar sessions. So uh, let me first introduce to the speaker, Mr. Sagnick Mukherjee. Actually, he is now in USA, but he is from Newtown, our local boy. He completed his schooling from KV, Kendriya Vidyalaya 2, and then BSc and MSc in Presidency University. So during that time, he visited SN Center several times, and participated in many programs. So after MSc, he has moved to USA, and now he is a fourth year PhD candidate student in Department of Astronomy and Astrophysics in University of California, Santa Cruz, where he is basically working on exoplanet and brown dwarf. So today he will be he will be talking on constraints on atmospheric dynamics and disequilibrium, terrestrial brown dwarf and exoplanet atmospheres. So I'm sure that you will enjoy that talk. With this one, let me invite Shadni for the talk.
Thank you. Thank you for the introduction and hello everyone. I'm Sagnick and I'm as Professor Das said, I'm a fourth year student and I was visiting my family is here. So I was visiting them during the puja after 3 years. So I was pretty excited to be here and I decided to come here and interact and talk about some of my research work with you all. So yeah, just a brief kind of telling you where I am from. And so this is my school. I did my whole school from the school just beside this campus, KV number 2. And actually, I was a regular participant of the Science Day celebrations at SN Bose while I was in my school. This was the place I first heard about exoplanets from Professor Das's talk. I first saw Jupiter with the telescope upstairs on the roof. I also gave my first scientific presentation here about 5 years or so ago. So yeah, I have been kind of pseudo connected with this place for a long time now. Academically, I did my bachelor's and master's from presidency in physics. Then I joined UC Santa Cruz. I'm the COVID batch of PhD students, so 2020 onwards. I mostly do theory of exoplanet and brown dwarf atmospheres, but my talk will also have a lot of observations, as I think observations are very important, especially for theorists. And on that note, I'm actually currently at Johns Hopkins as a visiting graduate student, where I'm learning observations and reducing data and kind of interpreting them as a Templeton Fellow. Okay, so to kind of introduce exoplanets, so in 1995, 2 years before I was born, these two gentlemen who got the 2019 Nobel Prize in Physics made the first discovery of a confirmed exoplanet. Now, what is an exoplanet? It's a planet which is not inside our solar system. It's revolving around some other star other than our sun. And the question then is, how do you kind of detect exoplanet? How do you know that there is a planet which is rotating around some other star? And unfortunately, I can't play this GIF, but this is called the radial velocity technique, which basically means that whenever you have a planet around a star, the planet will create some gravitational tug over the star. So the star won't be stationary. It will also have a little bit of a wobble. For example, because Earth rotates around the sun wobbles around a bit in a speed of typically 10 centimeter per second, which is a very tiny speed. But we all know that whenever a light source moves, we can measure its redshift and blueshift. So we can look, we can't see the planet because it's very faint. It's just a planet. But we can look at the star pretty well. We can measure its spectra over time. We can see the spectra red shifting and blue shifting. And from that measurement, we can infer that there is a planet. So that's what they did back in 1995. So it has almost been 30 years now. They got a Nobel Prize and they're superstars. And the planet they kind of discovered is called 51 Pegasi b. The naming is because the star was called 51 Peg or 51 Pegasi, and the planet is the B of the system, so it's called B. And this was not actually October 6th, so right around this time. And some of the interesting things about this planet is it has a temperature of 1,000 degrees, so it's pretty hot. It orbits its star in every 4 days, so it's very close as well. And the distance is about 50 light years from Earth. And this is just a comparison of a planet Jupiter. So it's puffier than Jupiter, but less massive. And the star is also a bigger version of our sun. So this is the first planet which was discovered outside our solar system. And this was a breakthrough. This opened the gates for 30 years of discovery. And just to we are on the same page, that this is not the only technique by which you can discover an extrasolar planet. This is the radial velocity technique, which was very successful early on, but then other techniques came along. All of these were GIFs. I'm sorry I can't play them, but you can get the sense that the transit technique is a technique where if you have a star and the planet is transiting the star, meaning it's between you and the star, then you would see a sudden dimming in the light from the star, and that's your transit. So the planet comes in front of the star, you have a dip, and then again a rise. And this dip, as you can imagine, is because the planet is blocking some of the starlight. So the dip would be proportional to the planet's radius. So larger planets would produce bigger transits than smaller planets. So this is another technique, but it's biased towards detecting larger in size planets, right? And then there's the direct imaging technique, which is actually the simplest to understand. You just go and take a picture and try to see if you can see planets. And this is an image of 4 real planets around a very far away star. The star is called HR 8799, and you can see 4 blobs of light around that star. The star has been blocked out because it's so bright that if you don't block it out, you won't be able to see the planets. And this is a very intuitive technique called the direct imaging method. So these are the workhorses of the field of how to detect extrasolar planets. And since that first discovery over the last 28 years, we have discovered planets after planets around many stars. And this picture kind of shows you the diversity we see. Now, imagine, before 1995, we only knew of one planetary system called the solar system. We knew that it had a sun, it had 8 planets, asteroid belts, and all these things. But now, in the past 28 years, we know of so many different planetary systems. The first thing when you look at this picture, this is not even the whole of known exoplanet. This is just a small subset. But when you look at this, what you notice is the diversity. Not every solar system, or not every planetary system is like the solar system. And that was a breakthrough in our understanding of how planets form, is the solar system. So we now are asking the question, is this a special case, or is this a general case? What's going on? Like what is happening with so much diversity in different planets, right? Also, forgot to mention, if you have any questions, just stop me and ask me. So you don't need to be formal. So now let's look at this in a more organized manner. We scientists don't love pictures always. We want to look at graphs. So the y-axis here is the mass of the planets in Jupiter mass. Okay, and the x-axis is their period. Now we know Kepler's third law that period can be kind of directly related to their distance from the star. So you can imagine a larger period means that the planet has a bigger orbit around the star. And this part is where Earth sits in. So Earth has a period of 300 days, about 300 days, and it has a mass of 0.03 Jupiter mass. So this is where Earth is, and this shows all the different exoplanets we know about. These are confirmed planets. These are not candidates. We know they are for sure planets. Around 20th April 2023, it's about 5 months ago. So this also is an outdated plot by now. But anyway, the first thing you notice is that each technique kind of detects different types of planets. Things like transits have detected all those green planets which are closer in, whereas radial velocity has detected these red planets. And the direct imaging has detected these blue planets here. The immediate thing you notice is that direct imaging detects planets which have very long periods because they are farther out. Because if they're closer in, then the star's glare won't let you see. You have to suppress the starlight with adaptive optics and everything. So close in is difficult with direct imaging. So yeah, this is kind of the number of planets and their properties we now know about. In fact, yeah.
Microlensing appears bit peculiar because it is detecting planets that have kind of similar period of 10 to the power
Yeah.
5,000 days or
Right.
something. Is there any reason for that?
I am not so sure about why that is the case. I think it's because that when you are doing microlensing, you're looking at some background star and its variation of its light due to the lensing event. So it needs the star needs to be have a certain separation from the planet's host star, most probably. That might be one of the reasons, but I'm not so sure why that is. I will have to
That
look.
could be a reason for lower bound, but why upper bound?
Yeah, I'm not so sure. Even so, the number of microlensing planets are very few, like they're not as much, and we don't know a lot about them right now. Generally, the workhorses has been mostly radial velocity and transits and direct imaging. But all these other techniques like microlensing, transit time variation, astrometry, they're in a very like they have not detected a lot, but they're still used to have some.
Yes, in case of that other
Sorry.
like radial velocity, you have sometimes transit.
Yeah.
For transit also
You
have
have
the
the
radial velocity.
Yeah.
Two-way.
Yeah.
In case of microlensing, do you have knowledge about the conform with the other?
I think you need to do like imaging.
Radial. So maybe you know all you do. You do that in high surface.
Yeah, but like right now with like better coronagraphs and bigger telescopes, we are able to like push. Uh, and this is about to become a big news with Roman telescope because Roman will be finding a lot of microlensing candidates, and then I think people will look at things like imaging to confirm those candidates. So this number is about to go up once Roman launches. Yeah, so continuing on, in fact, in last year's summer, we kind of crossed a milestone where we have confirmed 5,000 confirmed exoplanets. But now this number is even higher. So the story, the headline is that in the past 30 years, we are getting good and better in detecting exoplanets. Of course, not all types of exoplanets, but some. But let me kind of give you some highlights, some major kind of path-breaking discoveries we had in the field in the past 30 years. So the first of them is hot Jupiters. We knew about Jupiter, like it's a planet, it is about 125 Kelvin in temperature, it's about 5 AU from its host star. And then this is kind of the configuration of our solar system Jupiter, where you have Jupiter at 5 AU, you have Mercury at 0.4 AU. But when they first started finding these exoplanets, the first surprise was that you have this new type of things called hot Jupiters, which are of the size of Jupiter, of typically the mass of Jupiter, but they are very, very close to their host stars. Like a typical hot Jupiter perhaps is 0.02 AU. So that means you have a planetary system where you have a Jupiter as big as massive, but you have moved it much closer than the orbit of Mercury to its host star. In fact, I was kind of looking into what's the closest human-made things have been to our own star, and that is the Parker Solar Probe. The Parker Solar Probe is about to, I think, go to like 0.05 or AU. So a typical hot Jupiter is even closer to their host star than Parker Solar Probe is about to go to our sun. So it's really close. And this was a big surprise. How could you have a Jupiter-like massive planet so close to its host star?
So those Jupiters are also rocky?
No, so these are gaseous because their density is consistent with gases and not rocky planets. But we have found rocky planets as close as well. But these are not those. Okay, so this was a big surprise. We have found something which is not found in our solar system, something which just sounds bizarre. How could you have these kind of things? The next major discovery, in my view, is the finding of another type of planets called sub-Neptunes or super-Earths. So again, in our solar system, we have Earth and we have Neptune. But when we started to look at planets, we suddenly started to find a class of planets, which, so the x-axis here is the planet radius in Earth radius. So Earth is here, and Uranus or Neptune is about 4 times Earth. So Uranus and Neptune is here. But then we started to see that we asked the question, what is the most common type of planet in our galaxy? Is it Jupiter? Is Jupiter the most common planet in our galaxy, or is it a Mercury? So we asked that question. We tried to find that out, and we found that it's neither. Not even Earth. Earth is not the most common type of planet. It's something on a sub-Neptune, something which is smaller than a Neptune size, but bigger than Earth. And also super Earths are pretty common, right? Something which is bigger than Earth, but smaller than Neptune. So when we ask the question, what's the most occurring type of planet in our galaxy? Exoplanets, and all these detections told us that it's sub-Neptunes and super Earths. So imagine we have been looking at solar system. We have been thinking we understand everything about planets. And then suddenly we come to know that the most common type of planet is not present in our solar system because we don't have a sub-Neptune or a super Earth analog in our solar system. And something like Jupiter is actually not very common. It's not very likely to find a Jupiter when you're trying to pick a planet in random in our galaxy. So this was another kind of shattering discovery, and this came around. Sorry. So it would be around. Jupiter is around this, I think. It's around 9 Earth mass. Yeah. So it would be here. So it's not very common at all. It's kind of unlikely that you find a Jupiter. And then we could also ask the question that what's the probability of finding another Earth around another star? And it turns out that it's about 25% is the current guess, but it could be between 10% to 30%. So those are the things we are trying to answer in the field as well. And then the last thing, this list is not exhaustive. This is just 3 kind of highlights I put together. And the last thing is perhaps the most well-known thing about exoplanet field is the discovery of terrestrial planets in habitable zone of other stars. So what do we mean by habitable zone? I mean the region in your planetary system where water would be found in liquid form. It won't be gaseous or icy. And also there's something called runaway greenhouse effect, all those things, but we don't need to think about it. Just imagine this is our solar system. Okay, this is our solar system, Mars, Earth, Venus, Mercury. But if you make the sun a much smaller star, like an M dwarf, then what will happen is the habitable zone will also shrink. It will be much closer, just because the star is colder and everything. Then you zoom into this and blow it out, and we find this is the TRAPPIST-1. This is an M dwarf star, right? It's the coldest type of stars you can find, and we find not 1 but 7 planets around TRAPPIST-1 systems, and we try to measure the density. They are all consistent with densities of rocks. So we know that these are terrestrial planets in the habitable zone of another star. So this was a big news in 2016 and 2017. But since then, with JWST, we have tried to know that whether these planets have atmospheres, and we have been disappointed. We have found that these planets are bare rocks and they don't have atmospheres. That's perhaps because this star is an M dwarf, and M dwarfs are notoriously active, okay, throughout their lifetime. They in their pre-main sequence, so we think that has a lot to do with evaporating the planet's atmospheres, even if they had one. But now we are trying to think that these planets either have very tenuous atmospheres or don't have atmospheres. But this is one of the most exciting system in all of exoplanet science. In fact, I think some US senator asked the scientists, what's the most exciting thing you're looking forward to with JWST, and all of them said the TRAPPIST-1 system, whether these have atmospheres or not. So this is a big exciting thing which is still ongoing in the field. Okay, so moving on from major discoveries, now let me come to the goals. Why do we want to know about exoplanets? Why do we want to study them? And I think that's now fairly obvious. The first thing is to understand planet formation. Whenever you are trying to constrain your theory, your understanding, we astronomers love statistics. Now, exoplanet, our solar system is just one system, and we have built some theory of planet formation based on that system. but we need to know if that theory of planet formation applies to explain all these exoplanets we have found. Can that theory explain the presence of an hot Jupiter? Can our understanding of planet formation tell us why there are sub-Neptunes and super-Earths are the most common? So that's the #1 goal of the whole field, to understand planet formation. Now we also want to understand how planets work. How do they evolve over time? So we want to understand their time evolution, because I won't go into much details, but in solar system planets, there's much more difficulty because they're very cold and a lot of things condense out. So the physics is very difficult, whereas the exoplanets are hotter and they are in some ways easier to understand than solar system. Also, we want to understand their atmospheres. All of these planets either have or don't have atmospheres. If they have atmospheres, what are they like? What is their chemical composition? What is their physical state? We want to understand those questions. We want to understand the interior of planets. When you're going to the interior of a planet, it's extremely high pressure and high temperature. We want to understand what's the physics going on in these interiors, what's the equation of state of these interiors, and lastly, the grand kind of goal is to find an Earth-sized planet in the habitable zone of other stars, or something called the Earth 2.0. We want to find such a planet and we want to characterize that planet. We want to know if it has an atmosphere. And this last question is the goal of something called the Habitable Worlds Observatory, which is coming up in the next 10 to 15 years. Now, what I work on is these three things. Understanding how planets evolve over time, understanding atmospheres and interiors. But today, all of these are linked, by the way, but I'm still like making compartments. Today, I want to mostly talk about understanding atmospheres. How to understand or think about a planet's atmosphere. Okay, so I think I kind of went through this already. We want to understand how planets form, evolve, interior atmospheres, and just as to make us on the same page, there are the typical units. Uranus, Neptune has 15 Earth masses. Jupiter has 300 Earth masses. Just in case. Okay. Now, why is understanding atmospheres important? Because as the first question, remember we said that we want to understand how planets form. And the idea is that we can't always see planets forming in action. We can see them, but not always. The idea is if we understand the planet forms in this kind of a scenario in a protoplanetary disk around the star, then the idea is that some hints of this formation is preserved in the planet long after the formation has happened. So if we understand the atmosphere, the idea is that we can build back how the planet formed from that understanding. So that is one of the reasons. And then, but when you actually think about it in terms of number, if you think of our planet like Earth, and if you calculate what's the total mass of Earth which is in its atmosphere, and that number actually comes up to be less than 1%. So if you're thinking about Earth, a Jupiter-like planet, only 1% of its mass, or less than 1%, is in its atmosphere. Then why should we worry about something which is so insignificant? And the answer lies in this equation. If you have taken a stellar structure course in some form, you would be familiar with this. This is the equation which is the luminosity equation, which tells us how do we get the luminosity of a star, a planet, or a brown dwarf. And here are the terms. This is the luminosity, this is the nuclear burning, and this is the contraction over time, right? Now, in this equation, we want to know, this equation tells us how planets evolve, because this has the time. Depending on what these terms are, this time term is determined, and that would tell us if the planet evolves very fast, very slow, or in what way. So, why is the atmosphere important here? It's because the atmosphere is like a controlling valve, it's like a tap, which controls the evolution of the planet. Because your planet has formed out of it has some gravitational potential energy, right? It has formed with some gravitational potential energy, and it has nothing. So what it will do is, over time, it will try to lose that gravitational potential because it has no heating source. So it will lose that gravitational potential energy. But your atmosphere is sitting at the top of your planet. It's the last planet in this whole thing. So the heat needs to go out through this atmosphere. And if we do not understand the atmosphere, we won't understand how the heat is going out of the planet, and we won't understand how it evolves. So over time, the planet will contract. Some heat has gone out. That heat needs to go out through its atmosphere. So understanding its atmosphere is very important to understand how planets are evolving. For example, if you imagine that this atmosphere is very insulating, right, then it won't let the heat to go out. Then your planet will remain hot and puffy for a very long time. On the other hand, if the atmosphere is very transparent, it will let all the heat go out. It will cool down very fast. So atmospheres actually control the evolution of a planet over millions of years of time scale. Now the question is, how do we actually observationally study exoplanetary atmospheres? And that is an extension of the transit idea. That if you look at a planet crossing in front of the star, then you get one transit like this. Oh, I don't have the video. Oh, sorry. So the idea is that in each wavelength, if you look at the transit, you will get a different transit depth. Just because if your planet has an atmosphere, it will have gases, and gases absorb light at different wavelengths. For example, CO2 is very opaque at 4 microns, whereas water is very opaque at, say, 1.2 microns. So if you look at the planet's transit at 1.2 microns, and if it has water in its atmosphere, then it will appear bigger, just because the water will block the light from the star. Whereas if you look at the planet at, say, 3 microns, the planet will appear smaller, because the atmosphere is transparent, and the light can pass and reach you. So that is the idea of transmission spectroscopy. This is a real transmission spectra of a hot Jupiter. I believe this is the most, I was talking about this, this is the most impactful kind of science result from my 4 years career on exoplanet atmospheres I have been a part of. This is the JWST observed transmission spectra of WASP-39b, which is a hot Jupiter. And the x-axis is the wavelength, and the y-axis is the size of the planet in that wavelength. So imagine, as I was saying, say the planet atmosphere has a lot of carbon dioxide. And what will happen is, at 4 microns, the planet will appear big, just because it is blocking that light from the host star. CO2 is absorbing that light. Whereas in 3.8 microns, it will appear much smaller, as the y-axis is the size of the planet. And this is JWST data. And this is the first time we looked at so many gases in the atmosphere of an exoplanet. You can see gases like CO2, you can see gases like carbon monoxide, water vapor, sodium, methane. Methane is controversial, SO2. So we see that when we look at a planet's atmosphere, which is so far away, with things like JWST, we see that its atmosphere is made up of all of these different gases, right?
What is the clouds? Is it
Yes. So yeah, that's evidence that the planet atmosphere has clouds as well. Because if it didn't have clouds, then these depths would have gone to much deeper. So that's evidence that this planet's atmosphere has clouds in it.
clouds with dust particles?
Yes, dust particles, meaning most probably dust particles made up of silicates. Most probably. But this data does not confirm that. We need to confirm that differently. I will show that in a bit.
So 1 point.
Uh-huh.
You have a side which is the water blend.
Mm.
Water blend for my.
Yeah.
Then another is 9 miles.
Yeah.
Another is 2.7 miles.
Yeah.
It's a typical water blend.
Yeah.
So our understanding that CO2 generally inside the inside that. Here if you see the plot,
Mhm.
the size is much bigger on CO2.
Yeah.
That is the reason.
Yeah.
So the outside.
Yeah, so I think that's the reason is because this is a planet. So this is not actually solar metallicity in terms of its chemistry. It's much more enriched than solar metallicity because of ISIS kind of polluting it while it was in the protoplanetary disk. So this has a metallicity of 10 times solar, which means there's a lot more of carbon and oxygen.
Oxygen abundance is
Yes.
very less.
Yes.
So water very less.
Relatively less. Yes. Yeah. Everything is enriched than sun, but
Carbon is more oxidized.
yes. Yeah. Yeah. But
Carbon, of course, if carbon is there, it will have oxygen.
Yes.
they are more reactive.
Yes. And also I want to stress that one.
They're very interesting.
Yes. I want to stress that 99% of this atmosphere is actually none of these things. It's made up of pure hydrogen and helium. All these carbon dioxide, CO, that only constitutes less than 1% of its atmosphere. But hydrogen and helium is extremely transparent. Sorry. This is WAS 39. Yes.
You are looking at yes, yes.
Yeah. So what I did in this was, you see this line here, the model. The black is the data. So I modeled this data, and I'm very proud that I made this plot in my own laptop, which was, I would say, the highlight of my PhD.
So there are 1 second question.
Sure.
How is it really?
Yeah.
And you have a solid line in your model. Right?
Yeah.
Or is the you generate the model or it is
Yeah, so I have written my own. I will come into that in a second. I will explain how to kind of think about this kind of data and how to model it. So the short answer is you need to model a planet's atmosphere and all the processes going on there to model this kind of data. But actually, the most kind so before this data came along, people only knew up till this point. People have not looked at a planet's exoplanet's atmosphere beyond 2 microns per se. But when data came along, we were able to look up to 5.2 microns. In fact, this planet's data is now available all the way till 12 microns. So JWST has been revolutionary. It has given a complete picture of. This data is already public. Yes, you can already download it for. I think it has been public for the past 5-6 months. The other side of the data, I think, is not public yet, but it will come out very soon. But yeah, but we knew that CO2 should be there. We knew CO should be there. But what was the most surprising part of this data was this tiny bump you see here. You see a tiny bump, and we had no clue what gas is causing that bump. And the moment this data came along, all of us were kind of blind searching. What gas has opacity which can create a bump at 4 microns? And it was a blind search. We kind of checked all gases. And then we found that the best gas to explain this bump here is SO2. Now, SO2 is a gas which you should not expect in a planet like WAS39b unless there's a very specific process called photochemistry, which means that, because remember, this planet is very close to its star. So what is happening essentially is that the star is emitting X-rays and ultraviolets, which is going into the planet's atmosphere. It's breaking up gases like H2S and water and producing SO2 in its atmosphere. Now, this is the first evidence of photochemistry, first confirmed evidence of photochemistry in an exoplanet atmosphere.
you mean that layer of the what
Now,
layer or X-ray emission?
this is just X-ray, just not even flaring. Then if you just take the UV X-ray continuum and all those Lyman lines and all those things, and if you simulate what would happen to an atmosphere if you hit that atmosphere with those photons, then that tends to create this SO2 gas.
But in case of the, if you see that in the world, it's less likely the really don't produce the X-ray,
Yeah,
X-ray,
right.
UV,
Yeah.
large scale.
But the whole star of this planet is not a dwarf. It's I think a G dwarf or K dwarf. K star. Yeah. So that's what. Yeah. Yeah. So the thing is,
Another way is really flaring.
yeah. So that can happen too. Yes.
They
Yeah.
have a large number of flare per day.
Yeah.
Per day is a 90 flare
Right.
per week.
Yeah. Mostly like M dwarfs
Yes.
do that. Yeah. Yeah. Flares can do this as well.
Yeah.
But in case of this, you don't even need flares. If you just take the UV X-ray.
It's, yeah.
Yeah, it can be. Yeah, for sure. Yeah. We don't have a monitoring of the star itself, so we don't know if it flared or not. But actually, it did not flare, at least when the data came in, because we could see that in the transmission data, but it was not. So it might have flared earlier as well. But yeah, so this just tells you the power of JWST. It can open up avenues which were non-known anywhere before. And this result was kind of covered all around the world. It became a big deal, covered by New York Times, CNN, and even Anandabazar Patrika, which was a great thing to have in a Bengali news channel. Okay, so this is one way to observe an exoplanet atmosphere, which is observe its transit spectroscopy. But remember, planets have temperature of their own too. So you could look at its thermal light as well, kind of like a star, similar. So you can also do the thermal emission spectroscopy of a planet or a brown dwarf. You can look at the reflected light of a planet, which is when you go to upstairs and you look at Jupiter, you are looking at its reflected light. That you can also do for an exoplanet. It's hard, but you can do it. And you can do all these other things called direct imaging and phase, and all these are more complicated. We don't need to think a lot on this. But these are the different ways you measure an atmosphere itself. Okay, now coming back to the question that how to think about modeling such an observation. So what is the physics we need to think about when we are thinking about exoplanet or even brown dwarf atmospheres? Actually, and this is Jupiter in infrared. This is the kind of image we are taking of WAS39b in that spectrum. Okay, so the basic structure of a planet is that you have an interior, which constitutes 99% of its mass. Most of its mass is in the interior of the planet. And if it's a gas giant planet, it's mostly convective. The interior is convective because it's very dense. Density of a star goes as inverse to its mass. So the smaller the mass, the more density. Coming down to, when you come down all the way from stars to brown dwarfs and gas giant planets, the interior is very dense. So that's why it's totally convective. So that's the interior. And only 1% of its mass is in its atmosphere. Okay. Now, what is the physics you need to think about when you're thinking about this kind of an atmosphere? And the beauty of this is that you don't need to think about a different planet. You can think about Earth itself. If you're trying to model Earth's atmosphere, what are the different things you need to think about? The first thing is heat from interior. The interior has some heat because it's the heat of formation. For our Earth, is the radioactive heating from the interior of Earth. Then the atmosphere has gas molecules like hydrogen, helium, CO2, methane, water vapor, all of these molecules. The atmosphere can have clouds. For example, in Earth, it has water clouds. For some of these hotter planets, it doesn't have water clouds, but it can have clouds made up of silicates or clouds made up of iron. So it can have really exotic clouds in the atmosphere. And then there is a host star around the planet, which is kind of heating its atmosphere up. Yeah, and you need to think about all of these physics. And the moment you kind of draw this picture, you kind of realize that this is a very interdisciplinary science because you need people who understand how cross-section, row vibrational cross-sections of molecules work. You need to understand people who understand how clouds work. You need to understand people who understand how, you need to talk to people who understand interiors and radiative transfer and all these things. And then another process, which is kind of the science focus of my work, is dynamics. Remember, a planet's atmosphere is not static. It's always moving. That's why we have weather. That's why we have all these storms and everything on Earth. So all of this is also dynamics, dynamically active. So this is a highly coupled system. You can see that everything else is interacting with everything else. You have gas molecules, clouds, dynamics. Gas molecules are related to clouds. Dynamics is related to clouds. So this is a very much coupled system. Now, what are the important components? So the most important component is its temperature structure. By that, what I mean is how does the temperature vary with the height of the atmosphere? Then you also need to worry about chemistry because your atmosphere has molecules, so they are reacting with each other continuously. In Earth, the chemistry is nitrogen dominated because Earth is N2 and O2 and CO2. But in these gas giant planets, it is mostly hydrogen, helium, and some of these trace gases like methane, water, carbon, oxygen, and all these things react. You need to worry about radiation because radiative transfer is happening. Your radiation is coming up out from the atmosphere. The atmosphere has been hit by the star's radiation and all of these things. You need to worry about clouds. Clouds are notoriously difficult In fact, when it says on our phone that it's about to rain, and then you go out and see that it's not raining, why does that fail? That's because of clouds, because clouds are extremely difficult to model, even in Earth. That's why our weather predictions are not perfect. And then you have dynamics, which kind of couples all of this. So when you want to model this kind of data, you need to understand all of these different components, and not one by one. They are all covered, because temperature structure, if you change the temperature, the chemical reactions would change. If you change the chemical reactions, the gases would change. That would affect the radiative transfer because their opacity has changed. If you change the chemistry, clouds can change, because clouds are a byproduct of chemistry. And then dynamics can affect clouds, chemistry, and all of this. So it's coupled. It's very much coupled. Yeah. Yeah. So by temperature structure, I mean temperature as a function of pressure. So pressure is a dummy for height. We don't generally talk about height, but pressure, because these are all ideal gas and hydrostatic and all this. Okay. So then let me come to our model. So we have a model called Picasso. I am one of the lead developers of this model. And this model has all of this physics included inside it. It has cloud physics. It has radiative transfer. It has the chemistry necessary to model these atmospheres. It has dynamics and all those things. This is an open source model. Anyone can go and use this model to generate a model spectrum and compare with its data. And I actually wrote a major part of this model. This is all, by the way, Python based. So if you are scared of yeah, yeah, yes, yeah. So Jonathan Fort is my advisor. So yeah, yeah, yeah. So that yeah. Interestingly, this model actually started from modeling Uranus and Titan in our solar system. Then it moved. Yes, 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 yes. Yeah. So Picasso is a byproduct of that. So we, as a group, are now kind of. Yes, yeah. So we are. My advisor is Jonathan Fort. This model has been around for 30 years, but then we have improved it a lot in many aspects. Like we have improved the radiative transfer included in the model. We have improved the chemistry. We have improved the clouds and all of these things. So we are a big extended group. That's why I'm showing you all these different papers.
Marley cloud peaks.
Yes, Ackerman and Marley and all those things. Yeah. Yeah. So yeah, this is a huge, and this is not applicable to just giant planets. This can be applicable to brown dwarfs. This is applicable somewhat to terrestrial planets, and a lot of these. It has a huge. Yes, totally. Yeah. This model is on GitHub. Anyone can download and work. Sure, yeah, yeah, and we have very good tutorials as well, so you don't have to kind of be confused about the code or anything. So yeah, this is the model which we have been using to kind of model all these very interesting data sets. This is the logo of the model, and yeah, these are some of the features. It can simulate the reflected spectra of planets, thermal emission spectra of planets and brown dwarfs, transmission spectra, phase curves, one-day climate modeling, and this is the part which I have developed, including disequilibrium chemistry and photochemistry and all these things. So I have improved that aspect of the model. And the idea is that this model has all of these components, right? Now, so we have some theoretical ideas about what these components are. But this component, the dynamics, that's very complex, because you think of a planet which is 3D, which is rotating around its own axis, that has some very non-inertial effects and fluid dynamics and all those things. So that is the dynamic. That's why we have weather on Earth, right? Because of its rotation and all these things. So dynamics is extremely complicated. Now, how to study the dynamics in exoplanet atmospheres? This was a video showing what I mean by dynamics, something like convection, right? Planet atmosphere, even Earth's troposphere, where we are sitting, is actually convective. It's continuously overturning. That overturning is like noodles boiling in a boiling pan. The thing is, if we want to study dynamics in solar system, it's much easier. Again, this was a video, but we can see these things move in real time. We can look at Jupiter continuously. We can see the storms moving, forming eddies, and all of those things. Because we can resolve the planet, we can resolve the disk of Jupiter. But when we are looking at an exoplanet, it's just a point. We can't resolve it and study dynamics this way. So we need to find some other way. And that other way is by dynamics affects chemistry. So we can look at the chemistry really well and kind of understand what dynamics is in play. So it's kind of a back calculation. We're looking at the chemistry. We can do that pretty well. We're trying to understand what is the dynamics going on in this exoplanet's atmosphere. How is that possible? Think about a 700 Kelvin planet, and this is its atmosphere. And if you had no dynamics, just by chemistry, you would expect the gas CO to be buried deep inside the planet and not in its upper atmosphere. So if you look at the spectra of this planet, it should have a very small CO absorption because there should not be much CO in the upper atmosphere. But if you had dynamics, then what can happen is this CO can be dredged out. The dynamics can carry this CO to the upper atmosphere. And then if you take a spectra, then you suddenly see a big CO feature in the spectra. So by studying the chemistry really well, and by knowing the planet's temperature and all of those things, you can infer if the planet has a lot of dynamics or no dynamics at all. So that's the idea here. And the way to do that is extremely simple. You can kind of see dynamics is very complicated, but it's so little understood in exoplanets is that we can kind of simplify it. Because it's so uncertain, then let's start with the zeroth order. We can say that what dynamics does is essentially diffuses the gas in the atmosphere. It's like a diffusion process. And this is your diffusion equation. We have all seen this. And diffusion, the variable is the abundance of your gas, for example, CO. And then diffusion equation comes with the constant called the diffusion constant, which we are calling KZZ here. And by simple dimension analysis, you can say that if you have a sum KZZ, then this should be your time scale of the mixing, right? This should be a time scale because it should be inversely proportional to the KZZ, which means that if your atmosphere is very dynamic, there's a lot of dynamics, and KZZ is high, then mixing time scale is small because mixing is happening very fast. Whereas if your atmosphere is very slow, not very dynamic, then KZZ would be low and the mixing time scale will be very long because it takes a very long time to mix things up. So this is how we kind of simplify this whole very complicated scenario. Just because it's so uncertain, that is enough. Okay, so now let's look at how it actually works. So as Sir was pointing out, pressure. So the y-axis is pressure, which means this is upper atmosphere, this is deeper atmosphere, right? And the x-axis is temperature. And this is a temperature pressure structure of, say, a gas giant planet. Now let's look at the time scales. Okay, so the orange line is the dynamical time scale of the mixing time scale. In the convective atmosphere, there's a lot of convection, so a lot of dynamics. So that mixing is very fast. Whereas in the radiative atmosphere, there's not a lot of dynamics and mixing is slow. And then remember, every chemical reaction takes some time. When you're cooking food, it's a chemical reaction. It's not instantaneous. It will take some time. So this blue line is the chemical reaction time of methane converting to CO. And see, they cross each other at a certain pressure, right? Below this pressure, the mixing is faster than chemistry. And above this pressure, below this pressure, chemistry is faster than mixing. Above this pressure, mixing is faster than chemistry. And in physics, whichever process is faster becomes the dominant process because it's faster. So which means that deeper than this, chemistry will win because it's faster. And there will be chemical equilibrium. But above this pressure, mixing will win and chemistry will get affected just because mixing everything up much faster than the chemical reactions can occur. And what this means for our favorite gas CO is that if you didn't have any mixing or any dynamics, then CO would have fallen like this. There wouldn't have been any CO here. But if you have dynamics, then CO becomes constant above this pressure because it's been mixed up. Chemistry cannot destroy the CO. So which basically in plain terms, I just explained in much more physical physics, with much more physics of diagram I had shown you before. That if you have dynamics, then CO, you get CO in the upper atmosphere. And it comes in the spectrum. Okay, now let's look at spectra. What happens to the spectra? So this is an emission spectra of a gas giant planet or a brown dwarf. And again, you see all these bands, water, methane, ammonia, water, everything. And the blue line is when you have dynamics. And the orange line is when you don't have dynamics. And what you see is that the CO feature is very different between the two cases. If you have dynamics, you get a big CO feature. If you don't have dynamics, you don't get a very big CO feature. And this is the part we can measure really well. We cannot measure dynamics, we cannot measure anything. We can measure the spectra really well. Then from that we can measure the chemistry, and then from that we can back calculate what the KZZ or this dynamics parameter should be. And this is very important because dynamics affects clouds in the atmosphere, dynamics affects chemistry in the atmosphere, dynamics affects almost everything in the atmosphere. But the bad news is dynamics currently, this parameter KZZ in the exoplanet literature is uncertain by 8 orders of magnitude. We do not know what the strength of this dynamics in an exoplanet atmosphere is. It can be anything between 10 to the 2 to 10 to the 10 centimeters. That's an uncertainty of 8 orders of magnitude, which means all our models of exoplanet atmospheres are very uncertain because this parameter is uncertain. So the idea is now JWST, this amazing new telescope, gives us access to this whole spectrum. We can measure the spectra really, really well. What we want to do is go back, measure that spectra, calculate the chemistry from that spectra, and then infer this parameter so that we can constrain our models better about the atmosphere, which are about the atmospheres of exoplanets and brown dwarfs. Now, just to show you a quality of JWST spectra, this is the JWST spectra of a hot Jupiter. This is wavelength, this is emissions, okay? And here you see your CO2 feature again as an absorption. This is a spectra of a hot Jupiter. And it has a signal to noise of typically 5, even with JWST. It's a very noisy, even with JWST. And this is a JWST spectra of a brown dwarf, which are failed stars. And just look at the quality of the spectra. It has a signal to noise of greater than 1,000. And actually, when you really think about it, a hot Jupiter atmosphere is not very different than a brown dwarf atmosphere physically. So if you are a theorist, what would you go for to model that or this? I would always go for this, right? Because the data is so good that you can extract more physics out of it. So that's why to constrain this KZZ parameter, we first looked at brown dwarfs. Can we constrain the KZZ parameter in brown dwarf atmospheres? And just to give you a refresher on brown dwarfs, this is the luminosity in the y-axis and x-axis is the age, and this is showing evolution. So what is a star? A star is something which starts to burn hydrogen and stop its contraction. That's you see here. These are M stars. So they contract and then they become a constant. They have joined the main sequence. But what a brown dwarf is that something which never actually really fuses hydrogen. Its mass is so low, it doesn't fuse hydrogen, but fuses some deuterium. And it keeps contracting. So in this diagram, these are main sequence stars. And these are brown dwarfs, and all these things below this, these are giant planets. This just shows you what brown dwarfs are. These are failed stars, but more massive than a planet. Something in between a star and a gas giant planet. Something, a connecting link between Jupiter and your favorite star is a brown dwarf. And interestingly, brown dwarfs have temperatures, you see in this axis, very similar to some of these hot Jupiters. There's temperatures of 1,000 Kelvin, 2,000 Kelvin. So they are in fact very similar in many ways to planets, right? And as I was showing you again, this is another beautiful spectra of a brown dwarf with JWST. And look at the wavelength, 1 micron till almost 20 microns. And this dip here you see, this tiny dip, that's because of the presence of silicate clouds in this brown dwarf. I did the modeling for this work as well. This was ERS program for this brown dwarf. And yeah, this is the same plot. In fact, this is a spectrum of another brown dwarf, which has a temperature of 400 Kelvin. That means this brown dwarf has a temperature of your oven. Your oven is as hot as this brown dwarf. And you see that beautiful spectrum. All these different features you can see. Yeah, that's the silicate cloud. Now let's look at some similarities between brown dwarfs and planets. So brown dwarfs are No, JWST. JWST.
All are new.
Sorry.
All are new.
Yes, yes. This came out earlier this year. Okay, so just to make the point home, how are brown dwarfs similar than planets? Their gravity is different because they are more massive than planets. Their insolation is absent, so generally they are not orbiting a star, and even if they are, they're very far away. Their atmosphere is very similar. All of them have hydrogen and helium dominated atmospheres, which means their chemistry is similar. They have vertical mixing or this dynamics in all of these three cases. They don't have photochemistry, but planets have. And all of these things have clouds. So brown dwarfs are in fact very similar to planets in terms of their atmospheric chemistry, in terms of presence of vertical mixing, in terms of presence of clouds. And the data is much better. So the idea is first we ground our models on brown dwarfs and then look at planets. So that
Photochemistry absent from the direct imaging.
yeah, generally
Hard
yeah. So
that
the
is
most
only-
yeah. So the most yeah. So the most direct imaging planets are generally farther than 5 AU, or so it's very weak.
Yeah.
Yeah. Yeah. So that's what we did, but we didn't look at JWST data first. We first went back to archival data from Spitzer and a telescope called Akari, which was flown by Japanese in 2014, back when I was in school. And these data are from early 2005, 2006, but no one really looked at this data for a long time. So we went back, we looked at these data sets, and we tried to fit this data set with our Picasso model. So I have a paper upcoming on this work. And this is a model fit to one of the brown dwarf data. And you see that in the top, you see different gases. Like here you see the CO, here you see methane, here you see water and methane, and all these different gases in the data. This is one brown dwarf, and then this is another brown dwarf. So we fit the spectra of these different brown dwarfs with our models, and we did the first measurement of this very uncertain dynamics parameter, this KZZ parameter, in a brown dwarf atmosphere. So this is a plot showing the temperature of the brown dwarf in the x-axis, in the KZZ value in the y-axis. And the first thing you notice is the range. That's a log. So it's a huge range just because it's so uncertain. Then this is our measurement. So the solid lines you see at the top are predictions from just models before we saw them. And then we make these measurements. And what you see is that our measured KZZ values are much smaller than you would have predicted from just models, which again shows you the importance of getting observations, right? Getting all these wavelengths, which is so crucial. Now, these predictions were made assuming that the brown dwarf atmosphere is convective, whereas our data, the measurements we made, shows that the KZZ is much smaller than this case of convective. And it's smaller by 5 orders of magnitude, so it's a big difference. So this is a big result, but the bigger result is to explain why there is so much discrepancy, right? And I wrote a paper back in a year ago, which kind of hypothesized that sometimes what happens is our modeling suggests, not just our, this was suggested from 1997, Adam Burrows and group as well, that brown dwarfs can have not one convective and one radiative zone, but a sandwich radiative zone in its deep atmosphere. It just means that you are convective in the very deep atmosphere because the atmosphere is very opaque. Radiation cannot penetrate. But due to the wavelength dependence of opacities, what can happen is sometimes a sandwich radiative zone can form in the very deep atmosphere. And remember that the convective zone is very strong mixing because it's convection, right? It's mixing everything up. Whereas the radiative atmosphere is like Earth's stratosphere. Earth's stratosphere is also radiative. And we fly our planes in the stratosphere because it's not very dynamically active. It's very stable. So what then would happen is that the mixing would be high here, low here, high here, and again low. And what that can happen is the mixing time scale can look something like this. Very fast in the convective zone, slow in the radiative zone, fast in the convective zone, and slow in the radiative zone. and the quenching happens in this sandwiched radiative zone, then as an observer, what you would measure is not the KZZ of the convective atmosphere, but of the radiative atmosphere. And that would mean that you would measure a lower KZZ. But in fact, the KZZ is not low, but you are just measuring the KZZ at a place in the atmosphere where it's supposed to be low. So that's, yeah. So that's, yeah, go ahead.
Another question is that you are putting negative input.
Yeah.
Convective.
Yeah.
Is there some clue on that?
Yeah, so this, so we did not kind of bring this out of nowhere. We first saw this when we are doing this self-consistent modeling, and we first saw these radiative zones developing, and we know why that is. That's because if you kind of imagine the black body of each of these temperature, yes. So if you imagine the black body of each of these atmospheric layers, then this is hot. So the peak of the black body will be lower wave because this is hot. But as you are moving upwards, the peak of the black body shifts towards longer wave. And if it happens that the peak of your black body hits an opacity window where the atmosphere is suddenly transferred, just because molecular opacities are so high and low and high and low, then what can happen is you can develop this radiative. It's an interplay between how you are letting your radiative flux go out.
That that is theory.
Yeah.
London also.
Right.
It's like a giant.
Yeah.
Is it because of that zone?
So
focused by the pulsar during.
right. Okay. So this radiative zone you can develop even without no pulsation. So this is just an effect of how molecular opacity. But I don't know what will happen if there is pulsation.
Do you have some kinds of the 1 hour time scale?
Right. Very good.
Time variability.
Yes. 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 For sure. Yeah. Yeah.
That's no experience and really happen from the sport.
Yeah. Yeah.
Sport journey. This
Right. Yeah. Clouds or
still people use many around the globe, many in 1 hour.
yes. Yes.
Even Puri.
Yeah. Yeah.
I think Puri also strongly on this subject.
Yeah. Yeah.
But it's very difficult to explain that why this hours.
Right. Right.
Also, we had a difficult time to explain the referees. But some people is telling this scale, something on. Maybe one of the physics established that you
Yeah.
explain.
Yeah. Hopefully. So I have some news on that actually. So yeah. So this is the hypothesis, right? So you have this radiative zone. This is all theory. Now how do you get this radiative zone? So we ran a bunch of atmospheric models and all of that, and we created a grid. And the x-axis is the temperature of this grid, and the y-axis is the gravity of the problem. And we find that only in certain parts of this parameter space does this radiative zone exist. It's not present always, but sometimes. And it's interesting that happens to be between 450 Kelvin and about 1000 Kelvin. That's the sweet spot where the second radiative zone can form in these models. What this means is if an observer is targeting a brown dwarf which is landing on this spot, then he or she will measure a low KZZ because they are probing the KZZ in its radiative. Whereas if an observer is targeting a brown dwarf in this spot, it will measure a high KZZ just because of this. Now, how do we verify this? We are measuring low KZZ for these brown dwarfs. That's pretty good. And we have this hypothesis. Then how do we verify this? Then comes, this was all pre-JWST. And this is JWST data. And this is still not public. The paper is submitted. But you can see that our models can explain the JWST data even pretty good. This was the methane band in the JWST data. This is the CO2 band. And this is the CO band. And all of it. And what we learned from this object as well, again, from JWST data as well, is that KZZ is very low. So this is not a one-off data problem or Spitzer problem. JWST is also showing that the mixing is very slow in this object. And what I have as a news to add is that I am a PI of one of Cycle 2 JWST programs, which basically wants to confirm whether this radiative zone exists or not by choosing some targets in this part of the parameter space and some in this part of the parameter space. And our theory suggests that these objects should show us high KZZ, and those objects should show us low KZZ. And if that works out, then this theory of having a second relative zone would be proven or disproven. And yeah, these are the programs I am, yeah.
Another object temperature wise.
Yeah, so that's a good question. But the problem is that once you cross this 1000 Kelvin temperature, then clouds start to become important. Like some of these clouds come up in the photosphere. And once you have to deal with clouds, they are notoriously difficult because cloud physics is so difficult that it messes up your chemistry interpretations. So this is a sweet spot because these are something called T-dwarfs, where you can just measure the chemistry really well without worrying about
Its contents.
Yes, clouds are below the photosphere of these objects. So yeah, the first data is coming very soon from our program. It's in December. So yeah, we will be looking at that data and trying to verify this kind of hypothesis of these second relative zones.
In this evolution, how do you doing establish the relative zone will be your target?
Yeah.
But you will see that on the spectra.
Yeah.
From the spectra,
Yeah. So from the spectra, we can measure the KZZ. And we should expect if that relative zone is indeed present.
if it is low, then you
Yeah. So not just low. We want to see if these objects have low and these objects have high. Because
high.
yeah, that would kind of
Confirmation.
yeah confirm. Yeah. Yeah. Now, all of this was in brown dwarfs, but brown dwarfs are not planets. A lot of people get angry when you call a brown dwarf a planet. I like to call them planets because they're so similar, but brown dwarfs are still not planets. And the reason, the most compelling reason is because of photochemistry. Brown dwarfs don't have photochemistry because they are further out or isolated, whereas planets can have photochemistry. So the question is, can we extend this work to measure the KZZ in planets as well? So yeah, these are the three kind of processes there. And we are first looking at it theoretically, if we can do it theoretically. So this is a model of a planet, not a brown dwarf, a transiting hot Jupiter. And this is showing you the abundance of ammonia as a function of pressure. And the black line is chemical equilibrium, meaning no mixing. Whereas those three lines are different KZZs, very slow, medium, and very high KZZ. And one thing you see here is this tapering off. That's because of photochemistry, because photochemistry is coming and killing the ammonia molecules. When ammonia is a very weak molecule, a single bonded hydrogen. So photochemistry is killing that. So this is ammonia. So this shows that ammonia abundance is sensitive to KZZ in transiting planets. This is methane. Methane is not really very sensitive. This is HCN. HCN is very sensitive, but nobody has found HCN in a transiting planet yet. This is SO2. Remember the SO2 which was found in WASP 39b due to photochemistry. This is that molecule. It's also not very sensitive. And these are the temperature pressure profiles for our models, which is not really important here. But yeah, the spectra. This is a transmission spectra of these planets in these different cases. The black line is if you don't have any dynamics, no KZZ. But then the blue line is if you have a slow KZZ. Then you increase the KZZ, and the spectra changes, but very slightly. So measuring the KZZ in a transiting planet is much more difficult than doing it for a brown dwarf, just because the effects are smaller. And if you want to know what the amount, like what's the effect, then it's typically 70 to 80 ppm effect. And the noise floor of JWST is about 25 to 50 ppm, depending on who you ask. So if you want to do this for transiting planets, we would need multiple transits observations of the same planet so that we can beat down the noise and measure the spectra to very high precision so that we can do this. And that brings me to the last few slides, how we are doing actually trying to do this with the Manatee collaboration. This is a JWST collaboration. And we are getting data for a variety of planets. So the y-axis is planet mass, y-axis is temperature. And you can see that we have from massive planets to less massive planets, from hot planets to cold planets. And we are getting data from JWST of all these planets. And this is still an ongoing program. But one of the most exciting outputs of this program has been our second paper. So the TRAPPIST-1 doesn't have an atmosphere, was also a part of this. I was not a part of that paper, but I am a part of this. So we detected the first methane in an exoplanet atmosphere from this data. And you can see that this is the data and this is the methane signature. And we detected it both in transmission spectra and emission spectra, but we are reducing the noise on these data sets with multiple transits, multiple observations. And the goal here will be to do this similar kind of KZZ measurement as we did in brown dwarfs, but for transiting planets with this data in our models.
Do you have a higher spectra? 6.1 meter band.
Yeah, so Hubble has, I think, that spectra already. Yeah, yeah, but it doesn't. So the methane, there is methane, but the amount of methane is not that much. That has been a growing kind of problem. Why do you have
Evolving. Also
Yes.
evolving feature.
Yes, yes, yes. So that brings me to my last slide. So the key takeaway is JWST is changing everything. If you are, when I started as a grad student about 3 years back, we did not know half as much as we know now about planets. And in the next 2 years, the knowledge will grow exponentially. And these are the bigger kind of takeaways that we have measured KZZ, which has been really uncertain as a function of effective temperature. We think that we find that the KZZ is really low than the theoretical predictions, and we have a hypothesis, and we have similar upcoming observations and modeling to kind of check that hypothesis with JWST. With that, I would like to thank you for bearing with me for so long. Yeah.
So you have shown some spectra of exoplanets that are very close to the ground dwarfs.
Yeah.
So this is that how you distinguish between the exoplanet and the ground dwarfs.
Yeah, that's a great question. So the basic answer is by mass. We can, if you measure the mass of a brown. So theoretically, the idea is that anything which doesn't burn deuterium ever is a planet, and anything which burns even a slight amount of deuterium in a nuclear fusion, that's a brown dwarf. And if you kind of theoretically try to see at what mass an object starts to burn a bit of deuterium, that comes out to be about 13 Jupiter masses. So the distinction is basically everything which has a mass above 13 Jupiter mass is a brown dwarf, and anything which has a mass lower than 13 Jupiter mass is a planet. But this is a very artificial distinction. In terms of, yeah, like if something is 15 Jupiter mass, it is much more like a planet than a brown dwarf, right? A 70 Jupiter mass. But yeah, that's the distinction. So the basic distinction is by mass. Anything which is higher than 13 Jupiter mass is a brown dwarf, and lower is a planet.
So you cannot distinguish by the spectra analysis.
No, not much, because the only distinction would be if you could measure gravity from a spectra, but that is difficult because gravity only does not have a huge effect on the spectra, except some collisional induced opacities and all those things. So measuring gravity from spectra directly has been always hard. So that would be the only effect you would see. Otherwise, a brown dwarf spectra and a planet spectra would be pretty. So there are subtle differences, like the temperature structure of a planet would be different because it has a star, right? It's heating up the planet, whereas a brown dwarf doesn't have a star. So that would be different. But overall, chemically and physically, there's not much. You can use the same physics to model both of these things.
So you have shown some temperature profile structure of the planet.
Yeah.
So it has some dips. So this is due to the boosters.
Yes. So the host star kind of makes the temperature structure isothermal in the upper atmosphere, whereas a brown dwarf's temperature structure kind of goes like this, where a planet's temperature structure become isothermal because of the host star.
So what are the initial parameters that we have to put the model for the brown dwarfs?
So to make a atmospheric model, you need its effective temperature, its gravity, metallicity of the object, C2O ratio or some other elemental ratio, your favorite one, and things like KZZ. If you have clouds, the different cloud parameters as well. So those are the kind.
Also valid for the isolated brown.
Yes. Yeah. Yeah. For planets, you need some other things as well, like the host star. What's the temperature of the host star? What's the distance of the star from the planet? What's the radius of the host star? What is the metal? So for planets, there are some additional stellar parameters. But for if you have an isolated object, that's all you need.
After the survey. Private question.
Yeah.
Yeah.
So
Okay,
the
thank you.
KZZ, is that anything to do with the mass also? Is there?
So the KZZ is defined as the velocity of your dynamics times the length scale of your dynamics. So it's not dependent on the mass. Oh, you mean like the KZZ of as a function of mass?
Is there any relation at all?
I it's there should be a relation, but it's more like a twisted, not a direct relation, but it
Yeah,
would be.
some functional.
It should,
form.
yeah, it should be to temperature basically, because if you have a higher mass object and a lower mass object at the same age, then the temperatures would be very different. And a different temperature means totally different rates of convection and all of those things. That's how it should be, but not like a direct. What's it's like an implicit. You had a question.
Yeah, I wanted to ask what is the meaning of KZZ? Because your talk has a lot of KZZ.
Right. So KZZ is a parameter, some parameter, which basically describes how much overturning do you have in your atmosphere. Right. So if you have an atmosphere which has a lot of overturning motion, then it would have very high KZZ. Whereas if you have an atmosphere which is just static, not much is moving around, then it will have a very low KZZ. So that's the idea. Yeah, it's a parameter which parameterizes your ignorance, because dynamics is very complicated, right? It's not as simple as you have one KZZ parameter and that can explain all your dynamics. But right now, because it's so unknown, that you have to start somewhere. If you are familiar with like I remember like the accretion disk theory, there's some alpha parameters, someone kind of, so it's like similar. Like KZZ is a very uncertain parameter, but it's a very simplistic description of dynamics in an atmosphere. So you can have, and this came from Earth's atmosphere. So the Earth atmospheric people started this KZZ, and you can also measure the KZZ of Earth's atmosphere. In fact, I don't know if I have that slide, but I had a slide of KZZ for different planets like Earth, Venus, Mars. So, but yeah, simple way, it's just a dynamics. How much dynamics do you have?
Just to clarify, why the methane is controversial in batch like the data?
So the JWST data doesn't show a direct detection of methane. If you do something called a Bayesian analysis, you won't find methane in the data, but the best fit forward models still have a bit of methane. So it's not a confirmed detection. It's not a 5 sigma detection, whereas water, CO2, these are all 20 sigma detection, whereas methane is perhaps a non-detection. That's why I say it's not really, we don't see it is the answer.
Okay. Then, understand this better again.
Thank you.